carrying capacity of aluminum is influenced by several factors, including the specific aluminum alloy used, the dimensions of the aluminum component, and the direction in which the load is applied. However, a generally accepted rule of thumb is that the carrying capacity of aluminum is approximately 1/3 to 1/2 of that of steel. To illustrate this, consider two beams, one made of aluminum and the other of steel, both having identical dimensions. The aluminum beam, according to this rule of thumb, can support approximately 1/3 to 1/2 of the load that the steel beam can bear before experiencing failure or excessive deformation. This approximation is valuable in preliminary design stages for estimating material requirements. Several factors contribute to this difference in carrying capacity. Firstly, aluminum alloys typically have a lower yield strength compared to steel. Yield strength refers to the amount of stress a material can withstand before it begins to deform permanently. Steel generally possesses a higher yield strength, enabling it to bear greater loads without undergoing permanent deformation. Secondly, aluminum has a lower modulus of elasticity than steel. The modulus of elasticity, also known as Young's modulus, is a measure of a material's stiffness. A higher modulus of elasticity indicates a stiffer material. Steel, with its higher modulus of elasticity, deforms less under the same load compared to aluminum. This means that for the same applied force, a steel component will exhibit less deflection than an aluminum component of the same dimensions. Thirdly, the density of aluminum is lower than that of steel. Density is defined as mass per unit volume. Aluminum's lower density means that for a given volume, aluminum is lighter than steel. While this is advantageous in applications where weight is a critical consideration, it also implies that for a given weight, a steel component will generally have a higher carrying capacity. It is important to emphasize that this rule of thumb is an approximation and should not be used as the sole basis for final engineering designs. Actual carrying capacity must be determined through detailed calculations, considering the specific aluminum alloy, geometry, loading conditions, and safety factors. For instance, different aluminum alloys exhibit varying strengths. Aluminum alloy 6061-6, a common alloy, has different mechanical properties compared to aluminum alloy 7075-6. The 6 designation refers to the temper of the material, which affects its strength and hardness. Furthermore, the shape and dimensions of the aluminum component significantly influence its carrying capacity. A hollow aluminum tube, for example, will have a different carrying capacity compared to a solid aluminum rod of the same cross-sectional area. The loading conditions also play a crucial role. A load applied in tension will result in a different stress distribution compared to a load applied in bending or compression. Buckling, a phenomenon where a structural member fails due to compressive forces, is also a consideration, particularly for slender columns. Moreover, safety factors are applied in engineering design to account for uncertainties in material properties, manufacturing tolerances, and loading conditions. These safety factors further reduce the allowable carrying capacity of a component. To accurately determine the carrying capacity of an aluminum component, engineers typically employ a combination of analytical calculations, finite element analysis, and experimental testing. Analytical calculations involve using established engineering equations to predict the stress and strain distribution within the component under load. Finite element analysis is a numerical method that divides a component into small elements and solves equations to determine the behavior of each element. Experimental testing involves physically loading the component and measuring its response. For example, consider a scenario where an aluminum beam is designed to support a certain load in a building structure. The engineer would first select an appropriate aluminum alloy based on the required strength and corrosion resistance. Secondly, the engineer would determine the dimensions of the beam based on the load requirements, span, and allowable deflection. Thirdly, the engineer would perform stress calculations to ensure that the maximum stress in the beam does not exceed the allowable stress for the selected aluminum alloy. Fourthly, the engineer would consider potential buckling failures, especially if the beam is slender. Fifthly, the engineer would apply appropriate safety factors to account for uncertainties. Final design would ensure that the aluminum beam can safely support the intended load while meeting all applicable building codes and standards. In summary, while the 1/3 to 1/2 rule of thumb provides a quick estimate of the carrying capacity of aluminum compared to steel, it is crucial to conduct thorough engineering analysis and testing to ensure the structural integrity and safety of aluminum components. This analysis should consider the specific aluminum alloy, geometry, loading conditions, and safety factors. This rule of thumb is best used in initial estimations or conceptual design phases. Remember that structural engineering requires precise calculations and adherence to relevant codes and standards. The properties of aluminum alloys are impacted by temperature variations. Elevated temperatures generally decrease the strength and stiffness of aluminum, potentially reducing its carrying capacity. In high-temperature environments, specific aluminum alloys designed for elevated temperature service should be considered. Furthermore, corrosion can significantly affect the carrying capacity of aluminum structures, especially in harsh environments. Aluminum is generally corrosion-resistant due to the formation of a protective oxide layer, but certain conditions, such as exposure to chlorides, can compromise this layer. Proper surface treatments, such as anodizing or painting, can enhance corrosion resistance. Another crucial aspect is the type of loading. Static loads, which are constant over time, have a different effect than dynamic loads, which vary with time. Dynamic loads can cause fatigue failure, where a component fails after repeated loading cycles, even if the stress levels are below the yield strength. Aluminum is susceptible to fatigue failure, and careful consideration must be given to fatigue design in applications involving dynamic loads. When comparing aluminum and steel, it's also important to consider their joining methods. Aluminum is typically joined by welding, bolting, or riveting. Welding can alter the mechanical properties of the aluminum alloy in the heat-affected zone, potentially reducing its strength. Bolting and riveting can introduce stress concentrations around the holes, which can also affect the carrying capacity. The choice of joining method depends on the specific application and the desired strength and durability. Consider the application of aluminum in aircraft construction. Aluminum alloys are widely used in aircraft due to their high strength-to-weight ratio. However, the design of aircraft structures involves complex stress analysis, fatigue analysis, and consideration of environmental factors. The carrying capacity of aluminum components in aircraft is carefully determined through rigorous testing and analysis to ensure the safety of the aircraft. In automotive applications, aluminum is increasingly used to reduce vehicle weight and improve fuel efficiency. Aluminum suspension components, body panels, and engine parts are designed to meet specific load requirements while minimizing weight. The carrying capacity of these components is critical for vehicle performance and safety. In building construction, aluminum is used for windows, doors, curtain walls, and roofing. The carrying capacity of aluminum components in buildings must comply with building codes and standards to ensure the structural integrity of the building. Aluminum structures are designed to withstand wind loads, snow loads, and seismic loads. In electrical applications, aluminum is used for power transmission lines and electrical conductors. Aluminum conductors have a lower conductivity than copper, but their low density makes them a viable alternative in certain applications. The carrying capacity of aluminum conductors is determined by the cross-sectional area and the allowable temperature rise. The American National Electrical Code, or NEC, specifies the allowable ampacities for different sizes of aluminum conductors. NEC Table 310.15b16 provides ampacity ratings for conductors insulated at 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius in free air and in raceways. These ampacity ratings are based on the conductor's ability to dissipate heat without exceeding its insulation temperature rating. Remember that the actual ampacity of a conductor may be affected by factors such as ambient temperature, the number of conductors in a raceway, and the type of insulation. For example, if multiple current-carrying conductors are installed in the same raceway, the ampacity of each conductor must be derated according to NEC Table 310.15 current. This dating is necessary to account for the increased heat generated by multiple conductors in close proximity. In addition to ampacity, the voltage drop in an aluminum conductor must also be considered. Voltage drop is the reduction in voltage along the length of the conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. The voltage drop in an aluminum conductor can be calculated using Ohm's law, which states that voltage equals current times resistance, or volts equals amps times ohms. The resistance of an aluminum conductor depends on its length, cross-sectional area, and temperature. In summary, the carrying capacity of aluminum is a complex topic that depends on a variety of factors. The 1/3 to 1/2 rule of thumb provides a useful starting point, but it is essential to conduct thorough engineering analysis and testing to ensure the safety and reliability of aluminum structures. Remember to consider the specific aluminum alloy geometry, loading conditions, environmental factors, and applicable codes and standards. Always consult with a qualified engineer for critical structural designs.